Okay, so at any given moment we have nodes that are transmitting. These are the red guys here. We have nodes that are listening, but they could potentially be interfering if they were to transmit. Then we have one guy that you're interested in, so that's our desired transmitter. And then we have the receiver now, and then we have different questions now that need to be answered. So we need to know about the distances of these guys here, the positions of the nodes. We need to know who is transmitting. We need to know something about the channel states. And given that, we cannot assume that we have complete knowledge of all these things. No, there is a need to model this in a stochastic way and then get some average results. So that's kind of the typical assumption. Now, if we want to have something random now, then we use a Poisson point process. So this is typically how that might look if we throw in about 100 points in a 10 by 10 area. So that's sort of the generic model. So we take n random points in a square of area n, or yeah, that's a point process of intensity 1 in that area. So and as we can see, now there's a lot of randomness. So already here, that's kind of can be tough to communicate over or to sense now, because there is a lot of empty space. On the other hand, you have a bunch of guys that sit almost on top of each other. So this is the Poisson point process. So why is this a good assumption? Now, on the one hand, it's kind of a worst case. It's called what the people in stochastic geometry call complete spatial randomness, and of course it's closely related to the uniformly random distribution, where everybody is just positioned independently of each other. The other good thing is it is analytically tractable. It's certainly the one point process, homogeneous point process, that we can say the most things about. There are nice results now on percolation, connectivity related to the disk graph. We can say a lot about the distances. So kind of immediately now from the Poisson assumption, we can derive that for even in an m-dimensional setting of a general intensity, we want to know, we pick a random point in that space, or we pick one of the nodes of the point process, that doesn't matter. The distance Rn from a node to its nth nearest neighbor, that's distributed according to this, that's a generalized sort of a 3-parameter gamma distribution. And there is a coefficient here that is essentially related to the volume of the n-dimensional unit ball. So if we look at the plane, then the distance from a node to its nearest neighbor in particular follows a Rayleigh distribution with a mean 1/2 for unit intensity. So that's something good to start with. In terms of channel states, now sort of the favorite assumption is a Rayleigh fading. And that's also kind of a worst case now in terms of how the channel might behave. So if we take block Rayleigh fading, make that quasi-static, now then we have the received power being exponentially distributed with mean Q bar here. So if we transmit over a certain distance d, we use the typical attenuation model for the moment. Now we get the mean received power of transmit power times d to the minus alpha. We use I to denote the interference. So this is the accumulated power from all the undesired transmitters. And they, of course, are also subject to Rayleigh fading. And then with that, we can define a reception probability. So that is going to be a function of the single interference and noise ratio gamma. So we assume that the reception is successful whenever this ratio here exceeds a certain threshold theta. So the probability here is given by that expression. So the received power exponentially distributed is larger than this threshold times the noise plus interference. That's what we are going to use now. Here is this uncertainty cube. So we essentially have these 3 sources of uncertainties. On the one hand, we have the node positions, that can be either deterministically known. For example, in a lattice, we would be here at the origin. As we move out, that's kind of the worst case. That's the Poisson point process. Channel access, so here again in the center, would have strictly scheduled TDMA. And then as we get more and more random, now we get sort of the pure independent aloha model. And then on the other hand, in the third axis here, that would be the channel state. So here we have Rayleigh fading as kind of the worst case, and here we have just Gauss noise channels. So I'm mostly interested in the corners now of this cube. So for example, this one is an interesting one because it combines now the aloha, slotted aloha model together with Rayleigh fading and the Poisson point process. Yes? No, I mean the channel model. No, the channel model you can view it as kind of independent of how the nodes are distributed. But of course, I mean it depends on the environment. No, whether it makes sense to assume Rayleigh fading. No, but in this sense, no, I mean you can say something about all these points. And in that sense, I mean, all kind of combinations can make sense. And in that sense, yeah, you can view them as independent. So yeah, that's essentially summarizing. No, so we have the node positions. We could also, if you want to do that more quantitatively along this axis, now we could look, for example, at the relative entropy of a point process to the Poisson point process that has the largest entropy, of all homogeneous point processes. Channel access, now here we could also go along this axis in a continuous fashion by looking at how the transmit probabilities are correlated between neighboring nodes. And for the channel, we could use a more general model like Nakagami M fading and use the amount of fading, or 1 over n, to go from here to here. So we're not going to be considered too much with noise. So we say, okay, this is kind of an interference limited setting, and if we ignore noise, then there's no point in talking about absolute distances because everything becomes relative. So we can also just as well assume that the desired transmit-receiver pair always transmits over distance 1. And also for simplicity, assume that every guy who's transmitting uses the same power level. So if we wanted to change that and make that stochastic, we could incorporate the transmit power actually into the fading process. Okay, so what do we mean by outage and throughput? This is our network model again. So we need to know the interference at a given point in the network, given all these sources of uncertainty. And then the outage, of course, is when we are not successfully transmitting. So the probability of successful transmission from here to here, that's the success probability, and 1 minus that will be the outage. And then, yeah, as I said, we assume the distance here, the R0 between this pair we are interested in, we can usually assume that to be 1 and then just scale everything else accordingly. And then we have all the ordered distances to the potential interferers denoted by Ri. And then we have, yeah, we're coming to the throughput. So the S that can be strictly just 1 in a deterministic case, or it can be exponential with mean 1 if we want to denote Rayleigh fading. So that again, yeah, that includes the case of if we didn't have distance 1 and we did power control, then we would get the same result. So the total interference I, that if we sum up over all active transmitters, so we take that random variable S and multiply with the distances to the minus alpha, that gives us the interference again for the deterministic and the Rayleigh fading case. And we assume that packets are received if this exceeds the threshold theta, and this is our packet success probability. And of course, from this expression, now we can also see this is nothing but the cumulative, the complementary cumulative distribution of the signal to interference ratio. So if we have this probability, we also know the complete statistics of the signal to interference ratio. So now the throughput, now that's kind of the unconditioned reception probability. Before, the success probability, of course, is defined on the basis that the desired transmitter actually transmits and the desired receiver actually listens. So if we uncondition that, then we have to multiply the success probability by, in the Aloha case, by P times 1 minus P, which are the probabilities that transmitter transmits and the receiver listens, or if we have like a chain of nodes and a kind of an M-phase TDMA, so every m's node transmits, then we simply divide that by m. So this is what we denote by kind of the local throughput that we can achieve with unit parameters. I will come to that. I mean, now at this point it could still be finite, no. But now if we start to worry about actually characterizing interference, then we'll see that it's often convenient just to No. I mean, because it's really just the relative distances, no. you can play with the density of the network, and that's not going to have an effect. As long as you ignore noise, no, that would be destroying that property. Yeah. So we want to know something about the interference now, and conveniently we can use this shot noise model now that arose in the 40s and 50s now when people are characterizing noise in circuits. So we call it shot noise when we have like a Poisson sequence of impulses. So the TIs here, they would form a general, a conventional one-dimensional Poisson point process of a certain intensity mu. And this passes through a linear filter with an impulse response h of t, and we sum everything up. Then this I of t, that would be called shot noise. Or we can make that stochastic by introducing another parameter here, s, so that would be an IID random process that is independent of the Poisson sequence. So now why is that useful? Now we can pick as the impulse response, we can pick this power decay law that we have seen before, and then this in particular would be called a power law shot noise process, and then we just have to equate here what is here more kind of a time axis. Now we have to equate that with the distances and make it spatial, and then we can use that model. And then we'll often be interested in Laplace transforms because they're easier to get than actually distributions, PDFs or CDFs. So this is the Laplace transform of that, and then we can write that in that form, or make it more concrete. If we have this particular impulse response, so we go back to our model s times t to the minus alpha, we get this expression here, and we see the only thing that matters here in terms of the fading is actually this expectation. So we essentially go from 1 dimensions to 2 dimensions if we replace the time axis by the distances from the origin, where we assume that the desired receiver sits at the origin. So we get this Laplace transform here, and this is what has been known as an alpha stable or a Levy stable distribution with this characteristic exponent 2 divided by alpha. So these Levy stable distributions, they have the property, if we take 2 of them and we add them up, so we convolve them, they again return a distribution of the same type. So this is of course what we know from the Gaussians, but there's a whole family of these Levy stable distributions that share that same property, and the Gaussian is just a special case for a characteristic exponent of 2. So if we were to generalize that to more dimensions, we would see that this characteristic exponent in general is just the number of dimensions divided by the path loss exponent. So that generalizes to 3 and more dimensions. So these are these Levy stable distributions. In general, they have this kind of Laplace transform, and again for d equal to 2, this would be a Gaussian. We could put s deterministically to 1 if we wanted to analyze the case without fading. Now we have this expectation that shows up in the Laplace transform, and this is particularly simple. That's simply the gamma function of this characteristic exponent plus 1. So this is what we have in that case, and we can write that in this form. Now the problem is with this distribution is because necessarily this characteristic exponent has to be smaller than 1, which implies that this distribution does not have any finite moments, not even a finite mean. So why is this smaller than 1? Because we are dividing, d is equal to 2 divided by the path loss exponent. And the path loss exponent has to be larger than 2 for infinite networks, because otherwise the interference would be infinite anyway. In general dimension, the path loss exponent always has to exceed the number of dimensions of the network, otherwise we cannot make it big. Because if you accumulate interference, that will converge anyway. But the reason why this doesn't have any finite moments, that's not the same, but this actually comes from the fact that as nodes get closer and closer to each other, the interference grows larger and larger. So there are a couple of closed form expressions that are known. These are kind of special cases. So if we have a path loss exponent of 4 or a characteristic exponent of 1/2, in this case we get this guy here, and that's called this Gaussian or Levy distribution. And in that case, we can actually take an inverse Laplace transform, PDFs, CDFs. So this is the case that has been shown in the 90s. assumption that is often made now that oh, we have a whole bunch of nodes, we add up by some magic, from the central limit theorem, this has to be Gaussian. This is far from true. So if we wanted to look at what happens for aloha channel access, then we could just simply replace the density times p times the access probability, because in that case the set of transmitter is just a randomly thin version of the original process. If you look at the tail of this distribution, this is not Gaussian. The Gaussian case we know, of course, this decays exponentially, but if it's not Gaussian, then the tail of the PDF decays like a power function. And now this long tail is what sort of the culprit why this guy doesn't have any finite moments. So the long tail is due to the singularity now of this path loss law. So that's the problem, because nodes can be very, very close, and then you will receive a lot of power loss interference that causes a long tail. In practice, of course, this power law is not valid. Now, if we somehow were to eliminate the closest interference, or interference cancellation, or some type of error sensing, or whatnot, then this actually has a fantastic impact, because the distribution out of that interference mass loss, so it's the same. Yeah, plus phase.